the mic as well. So they're recording, so they've asked religiously pass it along.
You know what? You've seen the jacket. All right. Good morning, everyone. Byzantine agreement made simple. And if it looks complicated, it's only because I landed at 5 a.m. But otherwise, it should be easy. So let me remind you, Peace, Shostak, and Lamport is a beautiful definition. Is a protocol satisfying two properties: agreement and consistency. So there are some bad guys and some good guys. Bad guys have horns over there, and they are in a minority, 1/3, less than half, something like that. And so they start with a bit, and their bit may be different. So the agreement property means that at the end of the protocol, they should all agree, the honest ones, we don't care about, the bad ones may not agree to anything, on the same bit. And consistent means, by the way, if it happens to start with one bit already, they're already in agreement at the beginning with, then they should agree on that exact bit. Excellent. As Alessandro said, that is useful in distributed systems, is useful anywhere, and I actually went back to the source because I really wanted to have a new look at the public ledgers and cryptocurrencies, and I decided that I needed a super fast Byzantine agreement and very simple to program and do things. Good. So that is the problem. What is the communication model? Complete and synchronous network. Complete means here there is a fixed number of people, right, and players, and there is a direct communication line between all of them. And synchronous means we talk in rounds. At each round, a player I sends a message MIJ to player J, and that gets delivered at the next clock tick, right? That's good. The adversarial model is pretty scary, as it should be. So this guy has infinite computing power, can corrupt any player he wants, but overall no more, at any time he wants no more than n/3. Can totally control and perfectly coordinate all bad players, and also has the advantage of seeing what the good players have to say before instructing his bad corrupted player to say what he wants them to say. Okay. In all this business, there was an old goal that is really old. So essentially, we go back now to the 80s, and end of the 70s and 80s, and they say, can we reach agreement between tolerating a constant fraction of bad players in constant number of rounds? And turns out that if you do, your protocol has to be probabilistic because there is a famous lower bound by Finch, Lynch, and Patterson that say deterministically, if you have T bad players and you want to get rid of them or control them or handle them, you need at least a T+1 round. So, and in fact, actually, really, in Benor proved that you can tolerate in bypassing this lower bound for deterministic. It can actually have a constant expected rounds with tolerating square root of n players. And that really was the first time in which probabilism in a major computational model actually proved more powerful than determinism. That is really marvelous. And of course, the square root of n is not much, but Rabin raised it to n/4, still in constant count, but with a lot of assumptions, so from a cryptographic point of view. So it generated this notion of a common coin that was very excellent. However, this common coin is very powerful, but was provided externally by a trusted party. So then there were beautiful ideas by Braga, Chor and Cohen, which never quite solved the original problem, but they were very good anyway. So long story short, with my first PhD, Paul Feldman, unfortunately lost to science. He decided to do something else with his life. Great guy. But we had this n/3 bad player in expected constant number of rounds. However, via a very complex protocol. And in fact, a Katz and Co. that Alessandro said that takes 56 rounds to reach a consensus in probability a half. Ours was it was more efficient than ours, just to give you an idea. All right, so today we want to do better because somehow 30 years have passed, okay, so we have to do better. So our protocol is cryptographic, so they take the bad adversary that I described and scale it down to polynomial time, otherwise it's not going to work. And I want to tolerate n/3 bad players, and in 6 rounds, okay, using cryptography. By the way, cryptography before was actually used not to make things simpler or to make things faster computationally, but just to reduce or to reduce the number of rounds, but just to increase the tolerance for bad players. So, for instance, Dolev Strong already, really, literally 30 years ago, had this protocol that does not squeeze the number of rounds, but increases from n/3 to n/2 the number of bad guys you can tolerate. Okay, good. So we want to tolerate n/3 cryptographically very fast. So what assumption we need? We have 2 assumptions. One is a VRF, and one is a random string which is independent of the public keys. Everybody has a public key, otherwise we cannot do things. I don't want to tell you what a VRF is. That is going to take a good 5 minutes. And so let me tell you instead that is somebody that, at least in Bitcoin world, believes essentially that you can model hash function as a random oracle. And if you have such an hash function, and if the public key allows you to guarantees you that you only have 1 signature per message, then you are in business. That's all you need. So everybody has a public key, and there is a common random string. It's a very elementary setup. Okay, things process in rounds, 1, 2, and 3. At each round, there is a quantity that depends on the round and is unique to that random and random. And of course, because you start with a capital R is a random quantity, you hash it together with the local name of a round number 3, and you get a quantity Q3 unique and random linked to that round. So the protocol is essentially, right, we have to exchange a message. What message gets exchanged is all the trick. Okay? But I receive this BI from the preceding rounds. This BI represents the opinion of each player has about what we are likely to agree on. And we output an updated version of this BR, and at the end, this BR gets hardwired, right? So what message can we send, and what is the goal? Let me tell you the goal. Whatever goes here are instructions for doing 2 things. First, we want to make sure that this single message manages to put us in agreement, no matter how we start, with probability of third. Okay? Period. Single message, probability of third. I don't know if you've thought about this problem, but it's pretty good. Okay, it's pretty fast. And the second thing is that, by the way, if you get in agreement very fast, but you get out of agreement, that's not so good, right? Because you don't gain anything. So you also want to have a property that once you reach agreement, you stay there. It's a kind of, an attractor. Good. Okay? So let's see what of these things I want to share with you, what they look like. And say, first of all, not only you send your bit, what you think the bit was at the end of the previous round, but also a signature of this quantity QR. And you receive it from every willing player J. Why willing? Because the bad player may not send neither BI nor their signature. They can do nothing, right? So at least you can get it from the honest player and for some other bad player who is willing to send it. By the way, because signatures are unique, there are at most n signatures to worry about in total that you receive in the round. And then what you do? First of all, even though you have 2 things, let's focus on the bit. If you receive, say, the bit 0 from more than 2/3 of the players, then you locally decide on 0 and send it. That's it, end of a round. So in some sense, you can see that even though we have a signature up there, we actually ignore it. We don't use it. If you receive so many 0, stay with 0. Similarly, if you receive 2/3 ones, say 1 and forget signature and anything else. Of course, you may be in a situation in which you have not seen 2/3 zeros and you have seen not 2/3 ones. And that is the time, the else thing in which we start looking at this. We ignore the bits and we just focus on the signatures. And what do we do with it? First of all, you receive at the most n signatures, hash them. Therefore, you have what? A bunch of at the most n random 256-bit signatures. Why random? Because hash we are modeling as a random oracle. Why n? Because it's a single signature per person. And why 256? Because that's the favorite hash function gives you there. Okay, and what do you do with this? So now you have 2 n random strings at most that you've seen. I may see different strings than you. Each one of us, we have these random strings. You choose the minimum. These are strings. You can compare them. Choose the minimum. and the minimum we call rand_r, and I'm going to say this minimum is random. Why I put random in between quotes? Because each number is random, but the minimum is not random. So for instance, the first bit, right, if I look at the minimum, is more likely to be 0 than 1, right? So there is a bit of a bias towards 0 in the first bit, and there is a little bit of a residual bias on the second bit, right? But if you look at the last bit of this least significant bit of this minimum, of this rand_r, then I claim that essentially this is random as it gets. Okay, all this bias is essentially washed away. And so with probability 1, this is a random bit. And with probability 2/3 is a common random bit. So you don't know what this bit BR is from somebody else. But I know with probability 2/3, this bit is the same with me. Why? Because when at most n people give you a random string each, and the honest people will give this random string, and is unique, there is only one thing they can say. The minimum is attained by an honest person. An honest person always sends the string. So you always, if the minimum really resides with an honest person, everybody has seen it. And everybody therefore necessarily computes the minimum because the other guys have only one thing to say, they cannot change it. And the least significant bit is the same for you and me and everybody else. Okay, so that essentially is the protocol in its full glory. I want to say that's a very simple protocol. You essentially, you sign, right? You verify a signature and you do a hash and you count. The end. All right? So what we have to do, and which it should never be done in a 20 minutes talk, is to try to argue that this works. But I will, because it's so damn simple. So let me give you, if I somehow miss you, at least you get that zest that you are there almost, right, with probability 2/3, okay? Okay, so first of all, what do we want to do? Remember, I want to say is that if we happen to be in agreement on a bit, let's say 0, then an agreement on 0 is kept. And you know, let me prove it to you. Well, you remember the rule that if you have 2/3 zeros, you send 0 and you ignore everything else? Well, if you are in agreement on 0, which means all the good guys, which are at least 2/3, think of 0, they send 0, everybody counts at least 2/3 zeros, and everybody sends the same 0. Agreement is kept. Bingo. Okay, now let's say, assume that, well, you know, somebody sees 2/3 zeros, possibly nobody, or possibly everybody, and somebody else, what can I do? Can somebody sees 2/3 zeros and somebody else sees 2/3 ones? No, because more than 2/3 plus more than 2/3 is more than 1, is the pigeonhole argument, right? This cannot be. So what it can be is that somebody sees more than 2/3 zeros and or otherwise no strong majority for anything, or 2/3 majority for 1 and no strong majority for anything. So let's say the first case. If somebody, some good guys sees 2/3 zeros, then of course they will send 0. But if everybody else, therefore, has not seen this, and therefore what we'll do? We'll use the coin rule, because he cannot apply this rule. It's impossible that he applies this rule. So he gets this rule and sends what? A random bit. Now this random bit, with probability, I claim 2/3, it belongs to, originates from a good person, and with probability half is 0, so multiplication is 1/3. With a 1/3 probability, people decides on 0 and keep 0 in their mind, and somebody else decided to agree to switch on 0 for this coin rule. And therefore, all the probability 1/3, all the good guys are in agreement. Wow, that's it. Essentially, that is the zest of a proof. QED. Well, you know, this is not 6 rounds, because I try to agree, and then I try to agree, and then I get the agreement with probably 1/3 over and over again. At some point, I had to stop. So we had to be massaging a little bit more around. I will not disclose this. But what I want to discuss actually says, how come that this protocol has escaped us for 30 years? The problem is actually important. And if you try to solve Byzantine agreement you've never done, try it yourself, try to your students. If you tell them as an exercise, they will solve it. But if you tell it's a research problem, we're going to find it hard. And so the only thing that I reason is the following. The focus is that, you know, people before in the distributed community, The game was to do without cryptography, and therefore things had to be complicated. But now we use cryptography. But they also use cryptography. Yeah, but the distributed computation, they said, I want to do better than digital signature, because this is an implementation. I'm going to talk about authentication in the abstract. And the abstract should be better than the concrete, right? Any theoretician knows that. Wrong. So remember what Turing does. Turing, how do you do the recursion theorem? You say that any Turing machine is essentially a string. And then you actually use the damn bits of the strings to start manipulating. I'm doing the same thing. Because if I say that this message comes from Silvio, no question asked, or for Christos, or from Alessandro, or from Manuel, or from Scott, I cannot manipulate this because that's an abstract statement. But if you give me a signature, it's a bunch of string of bits, I can hash it. I can compare it. I can look at the minimum. I can look at the last bit. So I have something to play with. And that play gives me the power. I'd like to say that that is a piece with what comes next. We take this thing, as simple as this, and raise it to the level n over 2. By the way, it's much more simpler than the result of Katza and Co that Alessandro mentioned. And I want to say that this protocol actually is so simple that satisfies a lot of other properties as well. And one, it works in propagation networks, and these are somehow Bitcoin networks in very mysterious ways, which I have no time to describe. And then it satisfies particularly a property that I'd like to call player replaceability. And I'd like to say what this is. Everybody knows that in a protocol, it's crucial that me is me. So, because in a protocol, what I do? I keep state. I receive messages, and depending on which state I am, I'm going to send another message. And you do the same thing, so, right? So if all of a sudden I get shot and somebody substitutes me, can they do it in a regular protocol? No, because they don't know my state unless I put it on the New York Times, and even so I could lie, right? So it's really linked to the particular play. This TEM protocol has the property that if you shoot people and some people replace them without knowing anything at all, it works. And if you think about it, what you do, you are counting things that you have seen. If you tell them, disseminate it in the network or some other way, they will work the same way. So, right, the signature is a little bit more different, but still can be handled. In fact, actually, I believe, and I will at least I know that I can convince this guy, that is actually a protocol that you can use biologically to agree on things. Because organisms have to agree. Am I hungry or am I not hungry, right? I better decide, because I cannot stay here and go and have lunch at the same time, right? So we need to agree on things. But can we do digital signature? No, but this protocol, in this particular way, allows me to get agreement fast, whether it's in the brain or at another level. All right, all I can say, stay tuned, and thank you very much.
So you use the min function of all the hash of the signatures, the minimum. So why did you use the minimum? What's so special?
No, it's not so special. I need something that has the right property. So to say that allows me to select out of a bunch of things the honest one according to their cardinality. Right? That's what I want to do. I can use it also not according to the cardinality, but then I like to argue that with some good probability, you and I see the same thing. And by the way, notice that I don't get the minimum signatures, but the minimum of the hash of the signatures. And why do I make this difference? Because everything is simple, because you have to argue that the complicated stuff you can ignore. That's what makes the protocol simple. Because essentially, even though my signature scheme has a unique signature, if I want to be selected all the time, if I'm a bad guy, I could choose a public key whose signatures are unique, unforgeable, or forgeable, I don't care, but also very, very, very small. That is no contradiction for the signature is hard. So if a bad guy somehow makes himself, give himself as a signature, is going to be selected more often than he should. But if you hash them, and therefore you randomize them, and is unique, then there's nothing else to do. Right? Yep.
In your description, the fact that it was the most n over 3 didn't seem to play any big role. So if it was like 40% or 45% bad guys, does just the number of rounds go up?
No. First of all, remember that it did play a role in the pigeonhole argument, right? Because I'm going to say I have only two bits, 0 and 1, right? And I have to argue that it cannot be that some honest person sees n over 2 zeros and somebody else sees n over 2 ones, right? And so now I have two options. The two of them must be greater than 1, so I have to be 2/3 and 2/3. That helps. It's not going to help right away with probability half. If you want to do probability half, you have to be something more clever, but not more complicated. That's what I'm doing with the node, right?
Okay. Any questions?
Your protocol seems to wait for, you have a bunch of independent probability 1/3 events, and your protocol finishes when the first time one of them happens. So why aren't you getting 3 rounds in expectation?
Oh, because the strange thing that happens here, okay, remember, that's the protocol, and I'm saying, if I repeat ad infinitum, works. If I repeat 100 times, works. Why? Because everybody in this room knows that 1 divided 2 to the 100 is 0. Right? But okay, so we are fortunate guys, and we go fast places because we know these things. So, but now I have to do it 100 times. But I'd like to do it, I'd like to terminate the moment in which we are in agreement. And that's what is not clear to me, because if you just count things, now, do I know that we are in agreement? I do not know, right? So what do you want to do? You add to this thing something else clever, but not complicated, to make sure that this single message protocol now becomes a 3-message protocol in which you have a special round, call it coin 0, in which you agree, somehow it allows you to prove termination on 0. A special message, call it 1, that allows you to prove that you are in agreement if your agreement is 1. And another message called the genuine coin, that you say, well, if you're not proved the termination so far, you had to really go through the random step. And now we have 3 rounds, and then you see.
Is there a lower bound for the number of rounds for a probabilistic algorithm?
Yes, and I should have known them, but now my memory is not what it used to be, and never was that good anyway. So I believe that if you want to guarantee that you terminate at a given round, and that probabilistic or not, and that everybody terminates in that round, all the honest person, then t+1 is still a lower bound. If there are t bad guys, you have to wait t+1. Never mind if it's deterministic or not. I may take it back, because I've not seen, gone back for this, it's a long time since I looked at this. But I think this argument also holds. If you want to insist termination. Now notice that people here don't terminate at the same round, right? So for instance, if I've seen 2/3 of these guys, I know that the next time, first of all, agreement is never lost, but I know that I can terminate, but you terminate when the coin is 0, which will happen, and you end up again to see 2/3 of a guy. So you can see that is a staggered termination. So if you insist in guaranteed less fixed termination, that is impossible. Everybody simultaneously terminates faster than less than t+1 that is impossible, also probabilistically.
Keep more questions to the break, because we need to keep moving.
Right. Great.
Thanks, Steve.
Thank you.